Now, what keywords are? We'll see waves, energy transfer, transverse, longitudinal, frequency, speed, wavelength, amplitude. And by the end of the discussion, you'll be able to know the waves transfer energy. Use the terms like wave, frequency, wavelength, speed, amplitude, and period. State the difference between the longitudinal wave and the transverse wave, and you can give the example of each. So waves and how energy is transferred through waves. So waves transfer energy. You are standing by the seaside, you see waves coming every time. So they are transferring the energy from long back, thousands of miles away. Wave might have started, and that wave has given rise to energy transfer, and finally this energy has dissipated here at your footstep. So the energy transferred by wave can be considerable. This is what has happened. Enormous amount of energy which was being transferred through wave resulted in a catastrophic disaster. Huge waves, because these are energy. But waves have properties. Scientifically, if you want to know what is meant by the axis of a wave, if it is termed or seen like this, just try to imagine a wave that you see in sea. So this is how it is seen. The axis is the line running through the middle of the wave pattern. And this is a wave pattern. We call this line as the axis. Then what is meant by the crest of the wave? Crest is the top part of the wave. This is the crest. Then what is the trough? The trough is the bottom up part of the wave. Then what is the amplitude? You have seen the axis. Crest. This is axis. This is crest. This is trough. What is the amplitude? The amplitude is the distance from the axis to the crest or trough. This is your amplitude. This is your amplitude. Or from the axis to trough, both are the amplitude. So wavelength is the distance after which the wave pattern repeats itself. The distance between two identical points on the wave. These are two identical points. After this wave is going to repeat itself. So the wavelength means from this point to this point is the distance after which the wave pattern repeats itself. The distance between the two identical points. So the distance between two crests and troughs, these are also the wavelength. So the wavelength is we are pronouncing it as a lambda. Symbol is lambda. So whenever we write this, we are talking about the wavelength, the length of the wave, a unit length actually. Frequency. The frequency of the wave is the number of times the wave is in each second. The number of waves in each second, which is measured in hertz. Hertz. That means waves per second. Wave per second is what? Is the frequency. How frequent that wave is. We calculate the frequency of the wave. That is, if we have 125 waves passing a point in 10 seconds, so how many in 1 second? 16 waves passing a point in 24 seconds, so how many in 1 second? 30 waves passing a point in 1 minute, how many in 1 second? So the period of a wave is the time taken for one complete wave to pass a point. It is measured in second. Okay, let me go back and try to solve one of these for you. Say we have this one, last one we'll take. 1 minute, 30 waves passing a point in 1 minute. So, what about 1 second? In 1 minute, how many waves? 30 waves. 1 minute is equal to 60 seconds. 60 seconds. How many waves? 30 waves. 1 second. How many waves? 30 by 60 waves. That is half of 0.5 waves. That is 0.5 per second, 0.5 waves per second. That means 0.5 is the frequency. Period, again, the period is of a wave is the time taken for one complete wave to pass a point. So frequency and period, the link between the frequency and period of a wave is nothing but F is equal to 1 by T. T is equal to 1 by f. So frequency is nothing but 1 upon the time, that is the period of the wave, or the period of the wave is nothing but 1 by the frequency. Let us rearrange. T is equal to 1 by f. So these are the longitudinal waves or longitudinal waves. So in this type of wave, particle vibrate back and forward along the direction the wave is traveling. So this is how it is seen. This is longitudinal waves. A sound wave is a longitudinal wave. Sound wave is a longitudinal wave. And what about this type? This type of waves, the particle vibrate at right angles to the direction of the motion of the wave. If this is the direction of the wave, you can see that these particles are moving or oscillating, vibrating at right angle to the direction of the motion of the wave. We call these waves as transverse waves. Light and all forms of electromagnetic radiations are transverse waves. Light and electromagnetic waves or radiations are transverse waves. So, we have seen the wavelength and frequency. Now, electromagnetic spectrum. And we are going to learn, we state the order of wavelength, the members of electromagnetic spectrum, gamma, X, ultraviolet, visible, infra, microwaves, TV and radio waves. We state the radio and television signals. These are transmitted through air at 3 into 10 to the power 8 meter per second. That light is also transmitted at this speed. So electromagnetic radiations or signals and light both at this speed. So what do you know about waves and light and about the electromagnetic spectrum? You have known about waves and light by now. Now electromagnetic spectrum. The myth or reality, visible light is the only type of light. What you can see is what you observe. So what is radiation? All radiation is harmful. Is it so? Where does light come from? Light comes from bulb or sun or stars or any other way. Maybe some other phenomena. So light is a disturbance of electric and magnetic field that travels in the form of wave. Light is a disturbance of electric and magnetic field that travels in the form of wave. So like all waves, it can be described as having peaks, troughs, crest and trough, frequency, wavelength, amplitude and a transverse energy. This is the electromagnetic spectrum for you, and these are various waves. This is a small portion, very small portion of the electromagnetic spectrum that you are able to see, the light bulb. So this is the visible range from 0.4 micrometer to 0.7 micrometer. And if you go to the left, we have infrared, microwave, radio waves. So the wavelength is increasing. The wavelength is increasing and the frequency is decreasing. Wavelength and frequency are inversely proportional. If one increases, the other decreases. In the similar fashion, if you go to the right side, you have ultraviolet, X-rays, gamma rays. Now the frequency increases, but the wavelength decreases. These are all the tasks. Radio waves of the order of soccer field, house, and radio waves, you are FM, AM. You listen by these waves. Microwave ovens. What about microwaves? Radar, radio detection ranging. Infrared, you find out people. You can detect things depending on the heat they produce. Then ultraviolet, you can find out the viruses. X-rays, you have some broken legs, so say you can find out the molecules with X-rays, gamma rays. See X-ray machines, gamma rays, radioactive elements you can find out. It becomes shorter and shorter. So the electromagnetic spectrum consists of all the different wavelengths of electromagnetic radiation, including the light, the radio waves and the X-rays, and all travel at the speed of light. This is radio waves. You can't see it, but still it is there. The longest wavelength and lowest frequency. Longest wavelength. Radio waves are longer than 1 millimeter. Those waves longer than 1 millimeter, they are radio waves. And radio wavelengths are found everywhere. In the background radiation of the universe, in interstellar clouds, and in the cool remnants of supernova explosions. Radio waves, radio station can use this radio wavelengths, say from 10 centimeter to 100 meter, that is 1 kilometer of electromagnetic radiation to send signal that our radios translate into sound. So this signal comes, the radio signal receives it, and it forces your speaker to vibrate. These wavelengths are typically 1 meter long in the FM band. So FM band, it is 1 meter long. Radio waves or radio station transmit electromagnetic radiation as they are transmitting now. So the radio station encodes a pattern on the electromagnetic radiation it transmits, and then our radio receive this electromagnetic radiation, decode the pattern, and translate the pattern into the sound that you listen. Then the microwaves, that is 0.1 to 10 centimeter. Microwaves. Microwaves, the basis of almost all space communications. Microwaves, this is your transmitter, this is your receiver. You have, say, a object, a satellite, where we have receiver, it receives and then retransmit, you can say. The basis of all space communications, microwaves. Infrared, from 0.1 centimeter to 0.00007 centimeter. Heat. The heat which is produced by any object, may it be you, may it be your toaster. So infrared then comes 0.1 to this centimeter. The infrared wavelengths are about same size as a single bacteria. Then comes the visible light. Visible light covers the range of wavelength from 400 to 700 nanometer. Our eyes are sensitive only to this small portion of the electromagnetic spectrum. Visible light, the sun emits most of its radiation in the visible range, which our eyes perceive as the colors of the rainbow. Ultraviolet radiation have a wavelength of 10 to 310 nanometer, about the size of the virus. Young hot stars produce a lot of ultraviolet light and bathe interstellar space with this energetic light, which is the ultraviolet. You have ultraviolet, UA, UV, UVA, UVB, UVC. These are the ultraviolet indicators. Then comes the X-ray. X-ray range in 0.01 to 10 nanometer, about the size of the atom. X-rays about the size of the atom. So they are generated, for example, by superheated gas from exploding stars and quasars, where temperatures are near 10 million degrees. Then comes the gamma rays. Gamma rays have the shortest wavelength of less than 0.01 nanometer, about the size of the atomic nucleus. Highest frequency and most energetic region of the electromagnetic spectrum, gamma rays can result from nuclear reactions taking place in objects such as pulsars, quasars, and black holes. This is how the frequency changes with the frequency spectrum. These are ionizing radiations. So these radiations have to be handled carefully. And these are non-ionizing infrared. Non-ionizing, that is infrared, microwave, all these radiations. You have to be careful with certain of these waves. The power is high. So we have R, M, I, V, U, X, G. You can learn by this. Radio waves, microwaves, infrared, visible, ultraviolet, then X-rays and gamma rays. Rabbits mambo in very unusual expensive garden. Radio, microwaves, infrared, visible light, UV, X-rays and gamma rays. Lowest frequency, highest frequency. Long wavelength, shorter wavelength. So all electromagnetic waves travel at the speed of light. So now the transverse waves, in this type of wave, particles vibrate at right angles to the direction of motion of the wave. And light and all forms of electromagnetic radiations are transverse waves. We have seen this. Then we will see the speed of sound, distance and speed. So we'll be able to know the method for measuring the speed of sound in air using the relationship between distance, time and speed. We are going to describe how sound is produced. We'll be able to describe sound as a wave which transfers energy. And we will be able to explain what is meant by the frequency of a sound. Also, you can carry out calculation involving the relationship between distance, time, and speed in problems of water waves, sound waves, radio waves, light waves, and you'll be able to carry out calculation involving the relationship between speed, wavelength, and frequency for waves. So, what do we know about sound? All these are related to sound. Low sound, high sound. So, how does sound actually travel? How fast does sound travel? These are the ways to show the sound vibrations. So, the aim of this activity is to show how sound energy is produced. Just think, how is sound produced by this tuning fork? How does changing the length of the tuning fork affect the sound which is produced? Just look at the frequencies of the tuning forks. As the frequency increases, how does the pitch change? This is the energy transfer. You have a signal generator and here is your loudspeaker. So the aim of this activity is to show how sound energy is transferred. Just think what happens to the candle flame with the loudspeaker. What is moving the flame when your loudspeaker is on? This flame starts moving like this. So can you explain how sound energy is transferred? How fast does sound travel? You can use the sound switches and an electronic timer to measure the speed of the sound. So what two things do we need to measure to find the speed of the sound? Distance traveled and the time taken. So why is an electronic timer used when measuring the speed of the sound? Let us measure the average speed. Speed is equal to distance by time. Speed is equal to distance by time. We measure the time taken for sound to travel from one microphone to another, and we can repeat the measurements to improve the reliability. So, we have a microphone, we have electronic timers in these microphones, and a meter stick, just a hammer, and a metal plate. We hit on the metal plate and try to find out the time. The oscilloscope patterns and frequency, just think of this oscilloscope patterns and frequency. How is sound produced by this loudspeaker? At very low frequency, what do you observe? At frequency which is higher, what happens to the pitch of the note? What is the lowest frequency you can hear and the highest? Look at the signals produced for different instruments and different notes. So as the pitch increases, what do you notice about the number of waves on the screen? What is happening to the frequency? Just look at two notes an octave apart. What happens to the number of waves on the screen? What does this tell you about frequency? These are all examples. These are all practical problems. Just think, as the sound becomes louder, what do you expect to happen to the oscilloscope trace? Does loudness affect the frequency of the signal? So what can sound travel through? What do we need for sound to travel? It can travel through solid, liquid or gas. Sound can't travel through space because it is a vacuum. So when the air was pumped out of the container, it was no longer possible to hear the bell ringing. Right? This is also one of the examples. So longitudinal wave, we know that in this type of wave, the particles vibrate back and forth along the direction of the wave which is traveling. So a sound wave is a longitudinal wave. We measure the loudness of the sound in dB, decibels. Loudness of the sound in dB, and spending too long listening to loud sounds may damage your hearing. So be aware of the earphones you are using. Hearing damage in the workplace: if you are regularly exposed to noise at 80 dB or above, your employer must carry out your risk assessment, because if 85 dB or above, they must provide you protection, earbuds, etc. Maximum recommended length of exposure: 85 dB only 8 hours, 88 dB 4 hours, 91 dB 2 hours, 94 dB 1 hour, 97 dB 30 minutes, 100 dB 15 minutes, 103 dB 7.75 minutes, and 106 3.75 minutes. Only this minute. Nightclub is at 106 dB. 4 minutes unprotected, 2 hours protected. Gunshot is at 140 dB. Never protected. 15 minutes only protected. So is your music too loud? Preliminary data on these iPods and similar devices has found lower maximum levels above 100 decibels. The noise volumes of a chainsaw, risk of hearing damage after 2 hours, but not higher than 105 decibels. Say a football game in loud stadium, risk of hearing damage after 15 minutes. This is to fully understand the potential impact of these devices. It is important to know the sound is traveling a tiny distance from your earbud to your eardrum rather than being diffused in a football stadium or a concert arena. Ultrasonic. What is the normal range of human hearing? What do you know about this? So the normal range of human hearing is 20 hertz to 20000, that is 20,000 hertz, that is 20 kilohertz. 20 hertz to 20 kilohertz. This is the normal range of human hearing. What about ultrasound? Ultrasound is sound above 20,000 hertz, that is about 20 kilohertz. That is why you are not able to hear it. Then imaging with ultrasound. You might have seen ultrasound in medical imaging. Medical ultrasound used for imaging a fetus is between 1 to 20 megahertz. How is ultrasound used for imaging? A handheld transducer is held on the stomach. This changes electrical energy into sound energy, which is transmitted in waves into your body. And the waves are reflected off the boundaries between materials which have different sound properties. For example, amniotic fluid and the fetus. So the transducers also act as a receiver, detecting the echo and turning sound into the electrical signals. And by recording the time taken for the echo to be detected and the intensity of the echoes and using the speed of sound in tissue, a computer can build up a detailed image of the fetus. The skin, which is covered in jelly during the ultrasonic procedure. Why is this? Why you place ultrasonic gel on your stomach? The good contact is important. Otherwise, the ultrasound waves will simply bounce off the outer skin and no image will be obtained. So it makes movement of the transducer easier. It ensures a clear picture, which is what you want. So why is ultrasound used instead of X-rays? Because ultrasound causes no harmful effect to the fetus. It is low power, so can be used safely to image the fetus, not X-ray. They are dangerous. In high, prolonged, exposure, not good. Other uses of ultrasound. Doppler ultrasound is new technique which can be used to measure the blood flow. Ultrasounds can also be used to break up kidney stones, faster and safer than surgical removal. What about using sonar? Sound navigation ranging, sonar. This is used for underwater ranging. It was first patented in 1930, prompted by the Titanic disaster. So how does sonar work? What it is used for? Radio communication. What are radio and TV waves? They are a type of electromagnetic radiations that travel through air at 3 into 10 to the power 8 meter per second. So each radio station broadcasts with a different frequency or a wavelength. Remember, the speed is always the same, 3 into 10 to the power 8. And the frequency of the radio waves is much higher than the frequency of sound waves. Much higher. Imagine a wave where two waves pass a single point in 1 second. Frequency is what number of waves produced by the time taken in seconds. We already know that. Frequency, say 2 hertz. What is the time or what is the length of the wave produced in this time? 2 waves is 1 second. That means you have 2 wavelengths. So 2 wavelengths, that means 2 into 0.1, 0.2 meter. So this is your 0.2 meter. So 2 waves are proportional or produced in 1 second. That is 0.2 meter in 1 second. So this links distance and time, which gives us speed. How to calculate the wave speed? There are 2 formulas which can be used to calculate the wave speed. If the speed is a distance in a given time, so speed is equal to distance by time, you can calculate the wave speed like this. And calculating the wave speed, speed is equal to frequency into wavelength or c, and v is equal to nu lambda. Lambda f is the frequency, where f is frequency in hertz, lambda is the wavelength in meters, and of course your v is the speed in meter per second. So how fast is the radio or a TV wave? How fast is your TV wave? Radio and TV signals are part of electromagnetic spectrum. So this means that they travel at the speed of light, which is 3 to 10 to the power 8 meter per second. So this was the first part. We'll be taking more of this in the next section. Thank you so much.